Hello and welcome to Spur Economics. Today, we'll be discussing the Breusch-Godfrey LM test that can be used to detect autocorrelation or serial correlation. Please like, share and subscribe if you like our content. Visit the Spur Economics website for more knowledge on econometrics, link is in the description. The Breusch-Godfrey LM test can be used to detect autocorrelation or serial correlation in residuals of a regression model. The test is named after Trevor Breusch and Leslie Godfrey. We know that autocorrelation occurs when the error terms in a model are dependent on each other. That is, errors in previous periods influence the errors in the current period. Autocorrelation has serious negative consequences on the model coefficients and tests of significance. This means that it is essential to test for and detect autocorrelation. We discuss the causes and consequences of autocorrelation and the Durbin-Watson test for detecting autocorrelation in separate tutorials, links are in the description. The Durbin-Watson test, however, has some serious limitations in detecting autocorrelation. It is applicable to first-order autoregressive scheme only, that is, it can detect autocorrelation only up to one lag. Moreover, the model must not have lags of dependent variable as explanatory variables. The Breusch-Godfrey LM test overcomes these limitations of Durbin-Watson test. We can use it even when the lags of dependent variables are included as independent variables. More importantly, we can test for higher-order autoregressive schemes, that is, we can test for autocorrelation up to any number of lags. Let us consider a simple model with y as the dependent variable and x as the independent variable. In the model shown here, we have an autoregressive structure or autoregressive scheme of order rho. The error term mu is dependent on its previous row number of lags or row previous errors as seen in the equation. We can test for autocorrelation up to row lags using the Breusch-Godfrey LM test. First, we estimate the original model and obtain the residuals mu cap. We suspect these residuals mu cap to be autocorrelated of order rho. Next, we run a new regression with the estimated errors mu cap as dependent variable. The independent variables include the independent variables from the original model, that is, x in our example. In addition to x, we also include row number of lags of errors mu cap as the independent variables in the regression. We estimate the R-square of this regression with mu cap as the dependent variable. Using this R-square, we can obtain the test statistic as n minus rho multiplied by R-square. This statistic follows a chi-square distribution with row degrees of freedom. The null and alternate hypothesis of the test are shown here. The null hypothesis of the test states that the lags of mu cap are jointly zero, that is, all lags of mu cap are insignificant and there is no autocorrelation. On the other hand, at least one of the lags of mu cap is significant under the alternate hypothesis. We can test for autocorrelation with the Breusch-Godfrey LM test using the BG test function provided by the LM test package. In the command shown here, OLS is the object containing the results of the model. Our objective is to test whether the residuals of this OLS model are autocorrelated or serially correlated. The order option is used to specify row or the number of lags to consider in the test. Order equals 8 means that we are testing for autocorrelation up to 8 lags. By default, the function will apply the chi-square based test that we discussed. Apart from this, we can also choose the F version of this test by choosing type equals F. This can be used for F statistic version of the Breusch-Godfrey test. The BG test command shown here will report the chi-square test statistic, degrees of freedom and the p-value. The results are shown in the table. The degrees of freedom is 8 because we specified row or order equals 8. The LM test statistic is 17.311 and the p-value is 0.02703. Since the p-value is less than 0.05, we reject the null hypothesis of no autocorrelation. At least one of the lags is significant, indicating that the model residuals are autocorrelated. If you found this video helpful, don't forget to like, share, and subscribe to our channel for more in-depth discussions on econometrics topics. Leave your questions and comments below. See you next time.